Andrew Leech, embedded developer by day, electronics software tinkerer by night, who will be talking about profiling pathogens with MicroPython. Let's give him a warm welcome.
Thanks, Peter. And good afternoon, everyone, and thanks for coming. At Planet Innovation, we've been working with Lumos Diagnostics to develop a range of new diagnostics equipment, most recently leveraging MicroPython. This session, I'd like to take you on a bit of a journey through some of our learnings using MicroPython, and starting with a little bit of background, going through some of the challenges and learnings we've had, and celebrating some of our victories along the way. So Lumos Diagnostics works a lot with what's known as lateral flow assays. These are single-use point-of-care diagnostic tests. This Fabridex shown here, for example, works on a finger prick blood test, and within about 10 minutes will tell you if you've got a bacterial infection, a viral infection, or if you're unlucky, both. And it does this through the little stripes that show up or not there. Just read it by eye, very quick and easy to use. To assist people developing these tests and the medical groups around the world, Lumos, a few years ago, developed the Lilu Research Reader. This is a PC-connected USB device that images the test strips under development and assists via the PC app to develop the chemistry and science behind the strips. The other thing an imaging reader like this can do, though, is give you more than just a positive-negative result. It can actually give you a numerical or quantitative result. So instead of just a positive-negative, you can, say, get the hormone level of a particular marker in the blood, or by taking tests over multiple days, will let you know if an illness is getting worse or better. So the next logical step for Lumos was, how do we get these numerical results without needing the PC connected? So to build a device like this, we've got some requirements needed. We need a high-res camera. We need built-in image processing, ideally much lower cost than your typical lab-grade equipment. Obviously, it needs to be battery-powered. We wanted Bluetooth connectivity to a phone. And most importantly, it has to give exactly the same medical results as the PC app. So the important thing about our PC app is that it was written in Python. All the image processing and the algorithms have already been written and tested in Python. So around the same time as this was coming up, we came across the OpenMV project. This was a Kickstarter board running MicroPython and an embedded camera. It's got the camera there, it's got image processing, it's got low cost, so we're ticking a lot of the boxes. But out of the box, it's not automatically battery powered. It doesn't come built in with Bluetooth, and most importantly for us, it's not designed as a medical device. So therein lies the first question. Can we really make a medical device using something as relatively new to the industry as MicroPython? So to answer that question, probably should be very clear about what is a medical device. Well, a medical device is any device intended to be used for medical purposes. Thanks, Wikipedia. It's really useful. The Therapeutic Goods Administration of Australia has a more useful definition, where medical devices are used on humans, have therapeutic benefits, and more verbosely, generally have a physical or mechanical effect on the body and are used to measure or monitor functions of the body. So it's very explicit about what a medical device is going to be. And that's now very constrained about what you need to do to develop one of them. We make a lot of medical devices at Planet Innovation and generally follow quite a prescribed hazard and risk-based development process, which, to oversimplify it potentially, really comes down to identifying all the ways that device could potentially cause harm to the patient. In the case of a reader like this, the most obvious one is, if we give an incorrect result, we've got big problems. You could get an incorrect treatment and therefore doing harm. So everything to do with the development process is designed to minimise any chance of that happening. And that covers all disciplines of the development process, from mechanical, electronic, systems and software, right through. There's a prescribed process to help it. And everything boils down to making sure that anything that could potentially go wrong in the device is reported as an error, not an invalid result, just so that we can be absolutely certain we're not going to cause any harm. So back to MicroPython in medical. Get back to the question of, can a project like that have requirements? Of course it can. Have code reviews? Absolutely. Unit tests, functional tests, and importantly, be reproducible at runtime. And the test coverage of the MicroPython kernel gives us a lot of confidence of that. There's really nothing that magic about it. So through that process, we developed the Lumos camera reader. It's battery powered, it's self-contained, it's got the camera we need, it's got the image processing, Bluetooth connectivity with the Nordic chip, and most importantly for me, runs MicroPython. So to get back into the in-depths of it, there's what's known as soup in software, medical device. Has anyone here worked in the medical space at all? Quite a few. All right, so it won't be too new to those people. Soup is what's known as software of unknown provenance. As software developers on all platforms, we use libraries, code that someone else has written that we would like to inherit rather than redoing it ourselves from scratch. Unfortunately for me, most of that is not written in medical frameworks, so we have to be very careful about what we're doing with it. If it's an open source software, sure, we could potentially certify it ourselves. Review every line of code, whether it's 10 or 1,000 or 1,000,000. Not particularly fun. And if it's closed source, that's not even an option. Thankfully, the medical regulations, IC 62304, gives us a framework to actually use these libraries in a safe way. And it generally boils down to black boxing that library and containerizing it. We give it requirements about what we need out of it. We test it to all those requirements, which includes things like the interfaces, the APIs, and specifically which ones we're using in our product. And we make sure that everything we're doing with it gets to a case where we protect that library from us giving it bad data, and most importantly, any bad data it gives us back, we catch and limit the potential of it to cause harm. So for a reader like this, the obvious starting point here is that MicroPython, we can treat it as soup, and we can protect its boundaries and document that to show that everything we're writing and contributing to the product in the Python layer has a nice clear segregation to the MicroPython layer where it's protected and separated. So what if I want to bring in a nice small Python library again? There's plenty of good ones out there on MicroPython lib. Lots of them are small enough that we have just reviewed them and brought them in and maintained that soup boundary exactly where it was. And oftentimes that's quite easy. Just the same as every code piece that we're writing within our application itself. Or if it's a bigger library, such as Async IO, we treat it as soup as well, and you just update your documentation, update your test suites, and we can protect it and be sure that it works as needed. It gets slightly more complicated if you need to edit code past that soup boundary. So for MicroPython, we wanted to add an SD-RAM driver, because our board's got 32 megabytes of very comfortable RAM for us to use. The obvious initial option is to fork MicroPython and maintain our own fork forever and merge code back in and deal with all that, which adds overhead in future. So I've found it to be far more practical to contribute back. We all like open source. Let's contribute to the community. But it's actually a win-win for both the community and for the company, because through submissions back out, I've gotten free code reviews from technical experts in that platform and had much better code come out of it. And I don't have to worry about future merging upstream changes into our fork. So there's a whole maintenance headache that we just don't have anymore. And these things can be a really strong argument for commercial operations contributing back to the open source community if you've got a company that's more traditional or less open to that. Okay. I've been in embedded development for many years now, typically working in C. And the development process often goes through, we start writing some code, we compile it, we flash it to our hardware, we run it till we hit some breakpoints, investigate what's gone wrong, and write some more code. And we do that over and over and over until it finally works and we commit it. So the logical transition to MicroPython was to write the Python instead. We don't get to compile it, which is fantastic. And then we can just copy it to the board, but without the debugger that we're all used to, we're back to serial logs and printfs, which for a lot of people feels like a step backwards. However, with new platforms brings new opportunities. We can break that traditional slow embedded development cycle. Early in the process of developing this board, I found Jupyter to work exceptionally well on MicroPython. Are there many people here who haven't used Jupyter before? A good few. Okay, so Jupyter is basically a web-based Python environment for writing and running code live. It runs on your computer in the web interface, but runs the Python in a back-end server. Or, with a MicroPython kernel involved, it will run on your MicroPython board instead. So we've got the MicroPython kernel loaded for this particular workflow, and I've got, say, my early level prototype here that I need to start testing out. We can connect to the board, and this cell of code here, we can run that live, and can't see much, but it's just run it on the actual MicroPython board itself. So move back down, this magic cell, starting with local, is actually running on the local computer instead. So if I run that, we get IPython widgets. And we can interact with our hardware in real time, live. So on the off chance that's not already working the first time you write it, then you can just go back, edit your code, run it again, and now we get different behavior. So in this way, we can mock up and explore new hardware very, very quickly and develop all the low-level hardware drivers needed for your project. And in Jupyter, all the code you're writing is saved to your local disk, so it's protected, it's easy to reproduce. And then once it's working, simply copy it out into a regular Python module. All right. So most of us have probably been told for a long time we should be doing test-driven development. It never really stuck with me on the desktop. However, on MicroPython, compared to other embedded development approaches, it's shown itself to be incredibly efficient, largely thanks to the Unix port working alongside the STM port in our case and the other embedded ports. So the MicroPython unit test library is available, which works to basically the exact same interface as the regular desktop unit test. So you can write your unit tests once and run them on the board, or run them locally, or run them in your CI, and know that that exact same code works on all the platform you're developing for. In our case, with the image processing, it meant I could capture one image once on our target hardware, copy it across to the computer, and then very, very quickly develop all the image processing algorithms on the PC in small modular test suites and not have that slow compile, flash, run, debug cycle. So especially once your applications start to get a bit bigger, you can really speed up that process and you get your unit tests out of it basically for free. But it should still not discount the REPL. It's usually the place that people first start with MicroPython running in your serial port. And sometimes it feels like you might outgrow it pretty quickly, but it's still a very powerful debugging tool, even if you've got quite a large project running. You can even though there isn't a traditional inbuilt debugging, you can, to a large extent, fake it by having like irregular exceptions will break back out to the REPL. So at that point, you can be on your serial console and investigate the live state of the device and see what's going on. I found useful tricks being to write most of your device drivers as singletons, because you're usually only going to have one instance of them anyway. And that means even once you're back at the REPL, you can still access those drivers and see what state they're in and modify them live if need be. And it also really helps if you wrap up your main application in a function so that even once it's broken and it's stopped, you can restart it again quite easily if you need to. And a really good serial terminal can help a lot. Most of the ones that are targeted to MicroPython will auto-reconnect after restarts, or may have other bits of functionality to save and load, and can help speed up the development more than, say, the traditional PuTTY. All right, so say we've finished our development already. How do we now take that MicroPython board and actually ship it as a real product? We like having MicroPython there to develop it with, but we don't want our end users to see or even know that a REPL exists there. You definitely don't want them fiddling around inside your product while it's live. Thankfully, it's really quite easy to protect the world from the REPL and the REPL from the world. If you've got your main file running as an infinite loop, as would be typical in embedded, then really the only way to get out of that is through an exception. So if your top-level file catches that exception and, in our case, checks if it's a release build, if so, it'll just reboot it. So the REPL never really gets to the serial port, even in the first case. However, if you want to be really pedantic about it, the OS dupe term module can be used to connect the REPL to multiple serial ports or multiple inputs, or in this case, disconnect them to all. So now there is no live connection to the REPL at all. Therefore, your end users need never know that there is a MicroPython hiding deep inside your embedded chip. The other thing is you're probably not going to be shipping with a MicroPython board as a bare MicroPython board. So you probably want to brand it or build it customized for your product. Again, this is very easy to do without needing to edit MicroPython source code. You can start with the original board definition files, copy that folder out into your own folder where you can git, commit it, control it, and edit it, and build MicroPython against your board config folder. If you've worked with MicroPython before on a fresh install or after file system's been wiped, you'll see it gets pre-populated with a bunch of template files, which again, probably won't match your product. Once again, it's pretty easy to remove that from your customized build in your now custom board folder. You can replace the function that writes those files at startup with, in this case, a blank one, so you end up with an empty file system, or you can pre-populate it with your own files that match what's needed for your product's use. And if you're on STM boards where you've got native USB, you probably want to brand that to be your product. So when your user first plugs it in, it comes up as my special product, as opposed to you've just plugged in a MicroPython board. So again, within the board folder definitions, you can change all the USB branding and the USB IDs. Now, if you're working on an open source product, there's a really good website there, resource, that will give you a free USB PID ID code that you can use for your product. If you're on commercial, then you'll probably need to buy your own vendor code and not try and reuse the MicroPython one. So to get your application into the field though, as I was saying before, we've got the separation between the Python files and the MicroPython board. But ideally for production, we want to just flash it once. So in MicroPython, it's known as freezing your application code into the firmware image. Very similar to on desktop, you can freeze your applications with, say, PyInstaller. But if you, in this example, if you put all your files in your app folder and build your MicroPython image that way, it byte compiles all your app files into MPY, so they're a bit more efficient, and wraps them into the single firmware image that can be flashed onto the board during development and production. And then once it is in the field, those same files can be in-field upgraded via a built-in mboot bootloader, assuming that you've used that as well. So that gives you that functionality that, again, traditionally in embedded development, writing and maintaining a bootloader in the field is fraught with danger. But thankfully with MicroPython, we get a fantastic one for free. So we should use it. In short, MicroPython has been a great boon for this project, and we've been able to accomplish a lot very quickly. And really, medical devices aren't that different to any other device development. We've just got an enforced system of following best practices to ensure that we can't cause harm. The suit boundaries and the regulations around that mean we can use libraries and platforms that are already in the industry and in the field, use them safely and benefit from them. New techniques and new tools can replace older established methods of development and in many cases improve the development efficiencies. And MicroPython is actually quite easy to encapsulate into a professional product that no one need ever know has been developed on the cheap. Thank you, everyone.
Thank you, Andrew, for a very interesting talk. Do we have any questions?
How easy was it to make Jupyter notebooks connect to it like that?
It was easier than I expected, actually. There's a couple of Jupyter kernels already in the open, probably a couple of years ago when I started, that worked fairly well. But the one that I was using there is, so I should put a link up to it. It's the one that's on PyPy, Jupyter remote kernel, which I've developed myself on top of a lot of work done by GitHub user known as Goat Church Prime. But that, essentially, the Jupyter kernel there, it's just taking the text in the Jupyter boxes and feeding it through the standard pyboard.py raw interface to the board. So it generally works quite smoothly.
It looked beautiful. It looked like a game changer for embedded dev, just as far as usability.
Absolutely. It really was for us. It sped up that initial bring up on new hardware dramatically, and it allowed us to very cleanly put together a little test suite for all the different modules on the board.
Hi. The world of medical device technologies has not been scandal-free in the last couple of years. Have you experienced a lot of changes from that, or how is it do you find that you've now got more pressure on your development cycles and your product testing because of that?
It's a good question. The regulations behind it haven't necessarily changed that much. There's some new ones to do with security, certainly, and some aspects along the side. But I guess it comes down to how rigorously you follow them and make sure you follow the processes, which comes down to the company operating. In our case here, it's known as a Class A device, or Class 1. It's quite a low-risk device. There's no direct interaction with your patient, so it was fairly low risk to start with, which made it easier to bring a new technology in because we've got less to sort of prove. If I was writing code for a pacemaker, for instance, I probably wouldn't be taking such a big leap at one step. There's far more rigorous controls there. But for us at Planet Innovation, I don't really feel like there's been much change from them, but I think that's because we try and follow quite a strict process already.
Thank you. Great presentation. Just on that subject of security, is it possible to upgrade the software, say through Bluetooth, from end user if you've got the app or something like that?
The implementation we've got, I believe not, especially because the Bluetooth is on a separate chip altogether. So it's in a very much a sandboxed environment. And even if you lock up that chip, that can't affect the main processor that's handling all the actual medical diagnostic work. Bluetooth as it is it's not an easy protocol to work with, certainly.
Or USB, I don't know.
The USB is a good example too. And in normal operation, the USB interface isn't actually being used. In our case, if the USB is plugged in, it basically puts the unit into a different mode, either for charging only or for development use. So when it's actually running an assay standalone, the USB port isn't being used to prevent those sorts of interactions.
Thank you.
So I'm curious, since you've been developing embedded before Python kind of came into the space, have you found that doing it in Python kind of drastically reduced your development times, or do you think it's about the same?
I think the thing for us that drastically reduced the development time was the fact that we were inheriting a lot of Python code from our desktop app. And that's sort of most of the benefits of Python in general, is the ability to reuse a lot of code that's out there speeds up a lot of the practices, whereas there's never been the same sort of standardized system for sharing code in the C space. So you end up rewriting more that way. For this project, I've done quite a bit in the C MicroPython layer as well. So certainly there's been hiccups. I lost a few weeks on some file system issues, but they were all within that C driver space. So can't really blame Python for that. But certainly, yeah, the Python side and the developing more on the desktop, spending more time in that development loops on the desktop really sped up a lot of the otherwise laborious trial and error processes.
What kind of challenges did you face in proposing using MicroPython for a medical device?
It's a good question, and to be honest, it wasn't as many as I was expecting. I think me personally having an interest in it, I certainly got lucky. It sort of came along at just the right time, and in our case, OpenMV was tested by someone else at the company who was one of the more stricter people, and he gave it a good review. So I think, and it was still a fairly slow start to the process. We did there was a bit of investigation on that platform to start with, just to get a bit of a feel for it, and it took a while to, probably a few weeks or a couple of months to get enough confidence before really charge ahead. But there's being a fairly low-cost project to start with, and a low-risk product made it conveniently ideal one to start it with.
Yeah, cool.
We have time for one more question, if anybody has any. No? Well, let's thank Andrew again for one very interesting talk.
Thank you.